All right, I have started recording. Let's do this. All right, so what is the electric field at a point on the x-axis? I've got the setup there. Let's talk about which way the field is going to be because of the different particles. And let me color them different colors. We'll have Q1 will be blue, and Q3 will make red, just so we can have different colors to work with, make things a little bit more evident for ourselves. So we said, right, that positive particles, right, always produce electric fields that are radially outward. So if we look at Q1, right, and it's producing electric field that is radiating outward in all directions, right? When it gets to P, which is an arbitrary point on the x-axis, right? They want to know the electric field on the x-axis. Well, we have to pick a point to work with. So we'll pick a point P that is x meters, centimeters, whatever distance we're using away from the x-axis or the y-axis, the origin, whatever you want to call it. All right, so if we continue this, right, radially outward, we get the electric field from charge 1. If we look at charge 2, right, radially outward, electric field, right, its electric field will be E2. And if we look at charge 3, right, radially outward, we get the electric field of 3. So we have 3 superimposed electric fields, right? Electric fields that are all acting in the same space. And we're going to have to take those and add them together to figure out what the total electric field is. Right? We want to find the total electric field, so we're going to have to take those 3 points, or 3 electric fields, and add them together. A couple things that we can notice that will help us out when we're doing this, right? That'll make this a lot easier, actually, for us. First, the y component, right, because these are vectors, right, the y component of E1 and the y component of E3 are equal and in opposite directions. And if we have vectors that are equal in opposite directions, they cancel out. So the y component of the electric field from 3 and the electric field from 1 cancel. Second thing to notice, right, is E2 doesn't have a y component. Right? E2 doesn't have a y component, which means all that we have to worry about is the x components, right? We have to worry about the x component from E3, x component from E1, and the x component from E2, right? So this makes the problem insanely more simple for us because all we have to worry about is x components. We don't have to worry about y components. So let's set this equation up. We'll have the total electric field, I'll call it ET, is going to be equal to the electric field in the x direction, right? Because there's no y components, it'll be equal to the electric field in x direction. And the electric field in the x direction is going to be equal to the electric field from 2 plus the electric field from 3, just the x component, plus the electric field from 1, again, just the x component. All right, we can do one more thing to simplify this for us. The x component from E3 and the x component from E1 will be the same, right? Because they're at the same angle, they have the same value of charge, their values will be the same. So E3 in the x direction is equal to E1 in the x direction. And we can simplify that in our equation. So our total electric field is going to equal E2 plus 2 times, I'm going to work with E3, 2 times E3 in the x direction. We all good so far? I can't actually see the screen, so if you're not good, you're going to have to say something. Nobody said not good. All right, so I'm moving on. Okay, so we got to figure out the electric field from charge 2, and we got to figure out the electric field from E3 in the x direction. So let me do it separate, because that'll make it a little bit easier. E2 is going to be equal to 1 over 4 pi epsilon naught times Q over R squared. All right. That's pretty straightforward, right? These are all constants, so I don't have to worry about that. The charge is Q, right? So that's just going to stay the same. And the radius, how far is it away from P? Well, it's x, right? We said the distance along the x-axis was just x. So for E2, we'll have 1 over 4 pi epsilon times Q over x squared. All right, that one's pretty straightforward. That one's easy. 1 over 4 pi epsilon times Q over x squared. All right, E3x is a little bit harder. That's the best piece. Electric field in the x direction is going to be equal to, right, if we look at it, we want the x component of that electric field, right? We want just the x component. So if we look at angles here, right, we've got theta, we'll call that theta. If we look at the distance here, distance, we don't actually have a value for that, so we can assign a value for that, right? Let's just call that, oh wait, I'm doing E3. We want this distance, right? We don't actually have a value for that, so we'll call that R3. And it's going to be the, let's see, theta, so Cato, it'll be a cosine, right? So it'll be E3 times the cosine of theta. I do that right? Cosine theta, opposite over hypotenuse, multiply hypotenuse. Yeah, we're good. All right, so good start. We can substitute in for E3, right? Let's plug something in for E3. E3 is going to be equal to 1 over 4 pi epsilon times Q over our R value for this one we said was going to be R to the, or we'll just call it R3. So R3 squared times a cosine theta. All right. Cool, so far, we're good. Now, problem comes in here, right? Anybody know what our problem is? No, nobody knows what our problem is. All right, so here's the problem, right? They want to know how the electric field on the x-axis, right, given by a value x, right, when we know the distance the particles are apart. And the problem is this value right here for E3 is based off of a distance that isn't given in the start of the problem, right? This is a value we made up, and an angle that we also made up, right? So here we have a radius that doesn't tell us what d is or what x is, which is a problem, right? And we have a theta that's based off of d and x, but we don't know what d and x are. So we have two values in there that are kind of variables that they're too complicated for the question, right? The question wants the answer in terms of x and d, right? How far is it from the x-axis or from the origin, and how far apart are the particles Q1, Q2, and Q3, right? And this doesn't tell us that. So we have to rearrange some things, right? We have to substitute out R3 for values that are based on d and x, and we have to substitute out theta for values that are based on d and x. I'm still on the screen? I'm still on the screen, good. Okay, so I'm gonna take a second here. R3, how can I replace R3 in terms of d and x? Well, we can use the Pythagorean theorem, right? R3 is gonna be the square root of d squared plus x squared. So R3 is equal to the square root of d squared plus x squared. All right, so now I can replace here with d squared and x squared, and that'll get rid of my r to the third, or my R3. I don't know why I keep saying this to the third power. It's just R3, right? So we have a way that we can write R3 in terms of d and x. Can we write cosine in terms of d and x? Well, let's see. This angle theta, right, if we look at theta, we could do it in terms of x and R3, right? Cosine would be x and R3. And then we could use our substitution for R3 to get rid of the d as well. So cosine is going to be, cosine theta, sorry, is going to be equal to our adjacent, which is x, over our hypotenuse, which we just said was square root of d squared plus x squared, right? And now we have a way that we can get rid of cosine. So now we have to plug those two values in, right, to kind of get rid of what we're working with in terms of r and cosine. So our e value, I got 13 minutes, E3x, right, substituting in our cosine and our radius equations is going to be 1 over 4 pi epsilon naught times q over, instead of R3, I've got d squared plus x squared, but it's squared, so the square will cancel out the square root, and I'll end up with d squared plus x squared on the bottom there, times x, am I off the screen? I'm getting close. Over here, the square root of d squared plus x squared. And we can simplify that, right? Because we have multiplication on the bottom of the same thing. This is to the first power. This is to the 1/2 power. First power, because we're multiplying first power plus 1/2 power, will give us the 3/2 power. So we get our electric field is equal to 1/4 pi epsilon times q x over d squared plus x squared to the 3/2 power. And now I can take that and I can add it on over here. So plus 2 times the quantity, 1/4 pi epsilon times q x over d squared plus x squared to the 3/2 power. I got a little close there. All right, we good so far? Because we can do a little bit more to clean this up. All right, so I'm going to take this one more step, and we're going to have the total electric field is going to be equal to, both of these expressions have a 4 pi epsilon and a q, right? So I'm going to pull out q over 4 pi epsilon. What do we have left over here? Just the 1/x squared. Plus, here we have 2x over d squared plus x squared. No, yeah, I need that. To the 3/2 power. And all of that is in the I hat direction. I hat tells me that this is happening in the x direction, right? Because I hat is the x. Is that what they have in the book? Q over 4 pi epsilon naught times 1/x squared plus 2x over x squared plus d squared. Oh, they have x squared plus d squared. Oh, I forgot the square. You guys are just going to let me finish. I didn't put that second square on. To the 3/2 I hat. And this right here, right, will give me an answer no matter what the value of r is, or sorry, no matter what the value of d is, no matter what the value of x is, I can solve for the electric field at that point, right? And that'll work until x goes below 0, right? This won't give us an answer if x is below 0, but if x is above 0, we can get an answer for the electric field along the x-axis. And it'll work for positive or negative values of q, right? As long as x has to be greater than 0. All right, I'm going to stop recording, hopefully.